Okay. So how does this relate to fixed points? Well, what is a fixed point? Well, given a function, f of x, a fixed point, and it can be more than one, there could be multiple fixed points, but a fixed point is a special value I'm going to call it x star, just to indicate that it's not just any x. There's a special value x star such that f of x star is equal to x star. So it's just this kind of magic value that if you put it into a function, you get the same thing out. So here's the input, and here's the output for the same thing. So that's what a fixed point is. And I also like to break this down into stable and unstable. So this is stable if this is stable if f of x star, if you like plus or minus just a little bit, I'll just say like 0.01. And just for explaining, I'm using a specific value, but this could be basically any small value. So if this is closer to x star than 0.1, then it's stable. So this is indicating that you're getting closer to the value over time. Whereas this is unstable, basically, if this doesn't hold. So if f of x star plus or minus a little bit is further from x star than 0.1. So that's stable and unstable fixed points. So let's do an example. So the function that the function that this is based off of, the magic trick was based off of, is basically this function. You take your x, you divide by 5. And actually, let me do that in a different way. I think it's easier to think of it like this. So I'm still dividing by 5, but I'm thinking of it as 1/5. Take x, divide by 5, and add 36. So suppose I want to find the fixed point. And classify as stable or unstable. How do I do that? Well, it's actually pretty simple. Although very easy to forget how to do it. We're talking about so much stuff. But here's what you do: you take your function, and normally we set it equal to 0 to find the root, but not for a fixed point problem. For a fixed point problem, we set it equal to x. Do you see why? It's because we want our input, so we input the x over here, we want that to output, this is what we put in, we want that to get back out the same thing. That's what a fixed point is. You get the same thing in as what you get out. But this creates an equation that we can solve. So I might, various ways of doing it. I'm just going to clear the denominator, just to, who wants to deal with a fraction, right? So if I distribute this, I'm going to get 5 cancels with that 5, let's get x. 5 times 36 is going to be 150, 100 and, plus 30 is 180. And we're going to subtract the x here over, you get 180 is equal to 5x. And I'm just going to multiply by 1/5 on both sides. I guess I'm undoing what I just did, but oh well. Or divide by both sides by 5. Those cancel, and then get that x is equal to 180 divided by 5, which is, oops. It's not 45. What did I do wrong? Oh, this is supposed to be a 4. That was silly. It's supposed to be easy to do. Sorry about that. Let me try this again. I always make the stupidest mistakes when I have the video on. That's kind of a global rule of all of this. So subtract the x on both sides to get 180 is equal to 4x. So divide by 4 on both sides to get x is equal to 45. The magic value, once again. But to finish this problem, we have to classify it as stable or unstable. So how do we do that? Well, basically, you just take some. So if I plug in 45 into my function, I should get 45 back out. Well, actually, let me do this on Desmos. Desmos makes this really easy. So I'm going to type in my function here. So if I type in 45, I get 45 back out. Of course, that's what it means to be a fixed point. So that's great. To classify it as a stable versus unstable, basically you just have to like add a little bit, like 0.3, say. And then the question is this getting closer to 45 or farther away from 45? In this case, we get closer to 45 because 45.06 is closer to 45 than 45.3. So since we got closer to the fixed point, it's stable. So this is going to be S. So plug in 45.3. It doesn't have to be 0.3. It could be 0.1. It could even be 46. Doesn't really matter. As long as it's fairly close to 45. Plug this in, and we got 45.06. Sorry, I kind of fell off the screen there. But basically, what this means is it's stable. So why did the magic trick work? Well, stable fixed points basically kind of, as you iterate the function, as you apply the function over and over, they tend to, sometimes these are also called like attractors, so they kind of pull the value in. And this one actually pulls things in very quickly. So just applying the functions 3 times, you basically always end up with 45. The rounding also helps. I didn't talk about the rounding here, but the rounding helps it can kind of converge to 45. On the other hand, if it was an unstable fixed point, you wouldn't end up with 45. You'd end up somewhere else, or you might go to infinity, or it might do something else. But yeah, so stable fixed points are kind of nice that way. Another way, the way I kind of think about stable fixed points is actually like balancing a pencil. So if you're trying to balance a pencil on your finger, let me actually try doing this. It almost immediately falls off, right? That's an unstable situation. Because if you instead of being at 45, if you're at like 45.3, it's just going to fall off. So that'd be unstable. A stable would be like a pendulum, like a clock. You know, a clock, if you perturb it a little bit, it just kind of swings back into place. So that would be stable. Let me stop the video there.